So basically, all I wanted to say is that the arbitrarily small elements actually add up to be infinite. If we want them to get that power to help in the approximation. Because if I just say that B1 has arbitrarily small element, then the small guys may not have the power to to add up to infinite, and then it's basically no use. It's just like the previous problem. Then, so that's why I put this condition, because now when you put this, okay, and then you see this one converges. So this one converges, okay. This one converges basically means that the terms have to go to zero, right? It means that AIs and BIs have to go to zero. Okay, well, it means more than that, right? So we will yeah, it means more than that, right? Because if this series is converging, it means that if you take SI to be A1, I mean, yeah, A1 minus B1 plus minus B2 till AI minus BI, then this sequence is Cauchy, right? So even the tail, so even from a certain point, if you break the sequence, that also goes to zero, right? The tail is also going to zero. Okay. But then so basically these are the arbitrarily small elements captured. But then this one basically says is that the arbitrarily small elements add up to infinity, right? And this would actually implies that the AIs also add to infinity and the BIs also add to infinity. Because if one of them was finite and the other was infinite, then there is no way that this could converge, right? That is the whole point, isn't it? Yeah. So basically, to put all these conditions to make sure that the arbitrarily small elements also go to infinity is why we have put this condition. Okay, and arbitrarily small, we're trying to also capture in the fact that yeah, eventually the tail is going to zero. Now you can see it clearly works, right? Because now if you have an T, then you use the AIs to reach there, right? And then you use the BIs to pull back, right? Then you use the AIs to go forward, right? So eventually this error will go to zero, because what you're basically taking eventually is a part of the tail of the sequence, right? Eventually that's what you're doing, because you're always subtracting the BIs and adding the AIs. See, eventually basically just taking a tail of the sequence. Okay, so since the tail of the sequence is going to zero, this eventual error which is becoming the tail basically is also going to go to zero, right? And hence this will converge to T. Okay, so yeah, that's what basically what I wanted to say. But this is usually stated in a more better way, and it's usually stated as what is known as the Riemann rearrangement theorem, right? So this is essentially called the Riemann. What we proved right now is the Riemann rearrangement. So this is not the theorem. The Riemann rearrangement theorem says that if you have a series which is conditionally convergent, so this is conditionally convergent sort of, right? Meaning that without just with the signs it is converging, but if you make everything positive, then it doesn't converge, right? Right. So it's basically saying that terms of a conditionally terms of a conditionally convergent series, right, can be rearranged. So we are basically rearranging, right? Because we are taking more AIs first, then we are delaying and taking the BIs later, right? Can be rearranged, right, to reach arbitrarily close to any real number. Basically, that if you take all possible permutations and summations, then that will be dense in R. Right, so this is like the opposite of addition is commutative. This is like a polar opposite of that. Okay, so I hope that makes sense, right? Is that okay for everyone? Okay, all right, then if that's fine, then if there are no questions, then we'll move on to the next question. I guess that is the last question. So it was quite simple to state. Yeah, one second. So this means that the set of all permutations is dense in R. Um, yes, I mean set of all permutations of this series, of the terms of this series. That's what basically we showed, right? That you can find a subset which adds to that, and that's basically like taking a permutation, right? Because the tail is going to zero, basically. Yes, that's what it is. Yes. Set of all permutations means of this sequence. It's dense in R, not just R, but you can actually get to infinite also. So it is dense in R comma infinity minus infinity as well. This is a slightly better set in some senses. Yeah. So yes, that's what it is. That's a Riemann rearrangement theorem, but I didn't want to present it in that same old way. So just try to change things up, but yeah, slightly unstructured also. But anyways, so so now we will move